So this is my Rube Goldberg machine for physics class. It starts with a 10-kilogram ball attached to a pendulum by a 1 meter rigid attachment. It swings at 4.4 meters per second and collides with a 5-kilogram cart. It propels the cart at 8.854 meters per second to the right. The equation I use to calculate this for the velocity of the pendulum is the square root of 2gl times 1 minus the cosine of a, which is 2 times 9.8 for gravity, 1 times the length, 1 is the length of the pendulum, and times 1 minus the cosine of 90, which equals 4.427 meters per second. To calculate the velocity at the collision point, I used mv plus mv equals mv plus mv, and that left me with a velocity of 8.854 meters per second. The cart is attached with a wire loop with a diameter of half a meter, which is also propelled forwards with the cart. Behind the wire loop, there's a battery attached to a wire. This creates a magnetic field to charge to put a current through the wire loop. The voltage from the battery changes from 100,000 volts to 0.01 volts in 1.3 seconds. 1.3 seconds is the time it takes to get across a 10-meter track going at 8.854 meters per second. I'm ignoring friction because it is a cart with wheels, so it has very little friction. Along the path of the track, the wire loop gains a voltage of it gains a it has a voltage of 1.4 volts, and it carries 347 amps. This creates 376 joules of electricity to power this hot plate. This hot plate has a bowl with methane on it, with methane in it. The bowl of methane has a balloon over it. The balloon starts with methane gas in it, and it has a radius of 0.5 meters, so half a meter. As the hot plate is heated up, the more methane gas is released into the balloon, increasing the radius from half a meter to zero point 0.6 meters. To calculate all of this, I had to calculate the change of B for the wire loop, and I used 100,000 volts and 0.01 meters, which is the distance between the wire loop and the wire with connected to the battery for the first one, minus same equation but with 0.01 volts, which is the end voltage at 10 meters. And that gives me a change of B, which equals to 2. After that, I plugged it into the equation. B equals the change of B times A over T. And A was calculated to be 0.785, which is the area of the wire loop. This will give me a voltage of 1.4 volts. That's where the voltage came. That's where I got the voltage. Then I used the equation IVT equals E, and I had E, which was 549 joules, which is the required joules to heat enough methane, and that solved for 347 amps. Then to get the resistance in the wire, to know how many more joules I would need, was V equals IR, and that gave me a resistance of 4.03 times 10 to the negative third ohms. After that, I had to calculate how much the area of methane, the volume of methane gas that I needed to increase the balloon to be able to knock over the next ball. And I used the area of a sphere, which is 4/3 pi r cubed, and I subtracted with 4/3 pi 6 cubed minus 4/3 pi 5 cubed, which gave me 380 milliliters, which I needed to add to the balloon. After that, I used PV equals nRT to find out how many moles of methane I needed to add. So that tells me how many moles I needed to put in as liquid. And I calculated that to be 0.037. For that, I needed the specific heat of methane and the temperature difference, and that's how I calculated the moles. So after the balloon is expanded, it bumps into this next ball, which weighs 5 grams, so 0.05 kilograms. It is attached to a 2-meter rigid pole connected to a pendulum. So it revolves around the pendulum and collides with a 1-gram ball at the bottom. It is going 8.85 meters per second at the bottom of the pendulum when it collides with the next ball. For this, I use the same equation as the first pendulum, the square root of 2gl times 1 minus the cosine of a, except the numbers were a little different. I had 1 minus the cosine of 180 because it was going 180 degrees instead of just 90, and 2 meters. That was the length of it. After that, I used the same equation as before again. The m1v1 plus m2v2 equals m1v1 plus m2v2, and that gave me 44.25 meters per second. That is the speed of the 1-gram ball after the collision. This ball travels across some distance, and that distance doesn't really matter because I am negating friction because it is still a ball and does not have very middle. It's negligible friction. This collides with 2-kilogram bucket of water. To calculate this, I used the same equation again for collisions, but it was a bucket of water instead. The bucket of water after the collision moves at 0.22 meters per second, but the bucket was connected to basically a pendulum, it was connected to a swivelable pole, so that made it tilt and dump the bucket of water on Miss Schoonover's head.